This lesson is the first of 3 on the Inertial Reference System, or IRS. Between approximately 1970 and 1990, the inertial navigation system, which we studied in previous lessons, continuously evolved and developed. Instead of having a single standalone system with its own present position display, it became normal to have 2 or even 3 inertial sensors which pass their outputs to a central computer. Each of these inertial sensors is called an inertial reference system, and its outputs go to the flight management computer. The term inertial reference system, as opposed to inertial navigation system, is usually used if the reference datum is a ring laser gyro instead of a spinning disc type of tuned rotor gyro. We'll look at how a ring laser gyro works shortly. There are 3 main characteristics which define what we now call an IRS, which make it recognisably different from a first-generation standalone INS. These are greater system integration, use of ring laser gyros, and much greater computer power. We'll look at each one of these in turn to see what has changed over the last 20 to 30 years. The primary sources of information in the IRS are 3 ring laser gyros and 3 inertial accelerometers. Notice that we have 3 channels this time: forwards, sideways and down. This is in contrast to most INSs, which had only 2. The system needs to know initial present position. Unlike INS, it does remember where it was shut down at the end of the last flight, but nevertheless this needs to be refined by a fresh input of present position from the pilot. It also needs barometric altitude. As we just said, there is a vertical accelerometer and a vertical channel. However, on its own, the vertical channel is too unstable. The vertical accelerometer picks up the instantaneous changes, but the barometric information stabilizes the vertical velocity and altitude outputs. Other than that, all we need is TAS from the air data computer. As with the INS, TAS is needed in order to be able to compute wind velocity. Let's look at the outputs of an IRS and see how they compare with a traditional INS. This is an inertial reference unit. It provides the outputs for the aircraft's avionics. Firstly, it gives primary pitch and roll attitude. That was also provided by the INS. It gives both true and magnetic heading. We're already familiar with the idea that inertial systems operate in true because they align themselves by detecting Earth spin. The INS gave us true heading. However, whilst the IRS navigation and computing is all carried out in true, normal aviation practice is to use magnetic directions for all air traffic control instructions and airways information. Pilots therefore need to know their magnetic heading. The IRS, being more modern than the INS, has a greater computer memory. This allows it to have a database of latitudes and longitudes throughout the world, and the magnetic variation associated with each point. But variation changes rapidly near the magnetic poles, and the information becomes unreliable. The calculation of magnetic heading is therefore limited to latitudes of, typically, between 73 degrees north and 60 degrees south. Above these latitudes, only true heading is available. Acceleration is measured in the longitudinal, lateral and normal sense, in other words, forwards, sideways and down. Note that, unlike INS, we now need 3 accelerometers, not 2. Also, notice that the horizontal accelerometers are not north and east this time. They are longitudinal and lateral. The IRS gives angular rates of pitch, roll and yaw, just as the INS did. And it gives inertial velocities north-south, east-west and ground speed, as the INS did. However, it also gives baroinertial vertical rate. The IRS gives latitude and longitude position information, as the INS did. but it also gives a baro-inertial altitude. It gives wind speed, wind direction and drift, as the INS did. From this raw data, it calculates various items of secondary data which are used in the flight management system and the electronic flight instrumentation system, both of which we will cover later. Looking at the full list, the biggest changes to notice are the vertical channel and the availability of magnetic heading. In our introduction, we said that the first characteristic of an IRS, which makes it recognizably different from a first-generation standalone INS, is greater system integration. Integration is a word with at least two different meanings. Up till now, we have used it in its mathematical context in integral calculus to mean the opposite of differentiation. However, we will now use it in a more general, non-mathematical way to mean a system with many components which are interactive and interdependent. In the 1960s, aircraft were not generally designed as integrated systems. For instance, a large airliner would have been primarily conceived in terms of airframe and engines. Usually, instruments were thought about afterwards and were not normally specific to the type. Off-the-shelf items would have been used. The INS would certainly not have been designed in at the outset and might well have been retrofitted as part of a mid-life update. Nowadays, by contrast, an aircraft is practically a flying computer. Many of them are actually unstable or even uncontrollable in the event of a total computer failure. At the outset of a design of an aircraft, such as the Airbus 380, the chief avionics systems designer would have been a very important member of the project team. Modern aircraft are designed from the outset with the IRS as a central data source for many other systems. Inertial information is used in the flight management computer, the flight control computer, the thrust management computer, and the stability augmentation system. If you have studied the yaw damper, you will know that traditional yaw dampers have their own rate gyro. However, this is no longer necessary if the information is available from the IRS. Traditional weather radars also have their own gyroscope in order to keep the scanner horizontal as the aircraft banks. Otherwise, during the bank, the picture would be degraded as one side would be too bright, and the other side would be blank as the energy went out into space, never to return. Therefore, the scanner must be kept stable with a gyro. But instead of having a dedicated scanner gyro, these days the reference comes from the IRS. Ground speed is fed to the anti-skid auto-brake systems, and attitude information is used in the attitude director indicator, and navigation information in the horizontal situation indicator. The vertical speed indicator is rate-aided from the vertical accelerometer. This is sometimes called an inertial lead unit. And all attitude, acceleration, velocity and position information is, of course, continuously fed to the flight data recorder. Let's summarize what we've covered so far. There are three main characteristics which make an IRS recognizably different from a first-generation standalone INS. These are greater system integration, the use of ring laser gyros, and much greater computer power. The outputs of the IRS are broadly similar to those of the older INS, but with the addition of a vertical channel and a magnetic database. Modern aircraft are designed with the IRS at the heart of an integrated avionics system, which avoids duplication of sensors such as auxiliary gyros and other less accurate data sources. The next lesson will go on to consider the ring laser gyro.